Okay, today we're going to talk about the law of conservation of energy, and we stated something like this: if outside forces do no work on a system, okay, so no work on a system, then, and we state it two different ways, the total energy of the system remains constant. And you saw this in your labs or something close to it. Okay, so we could state this in equation form. That means that the initial kinetic energy plus the initial UG plus the initial spring energy plus any other initial energy we need to worry about has to equal the final kinetic energy plus the final UG plus the final US plus anything else, any other type of energy. The second way we can state this is that the sum of the energy changes and this is of different types of energy, is zero. So we could state that by saying that the change in kinetic energy plus the change in UG plus the change in US plus the change in any other type of form has to be zero. And depending on what kind of problem you're working on, one of these two formulations might be easier to think about than the other. Okay, so what this one here is saying is that if any energy increases, another must decrease. So we're going to talk a lot about mechanical energy in this course and in physics in general. And when we talk about mechanical energy, we're talking about kinetic energy, UG, and US. So spring potential energy and gravitational potential energy. When we talk about other types of energy, we're usually talking mostly about thermal, sometimes sound, and sometimes light. Okay? So we're going to kind of review the labs that we did. All right, so let's take a look at ULab 1. And in ULab 1, you got a graph, and hopefully it looks something like this. Okay? So we graphed energy in joules, we graphed height versus meters, and we should have seen a couple things here. Hopefully you saw that UG was increasing with height. Hopefully you saw that kinetic energy was decreasing with height. And you probably saw the total energy looked something like this, where it looked like it was almost increasing with height. But if you recall, we started with a really large height. So we started around here with a very large height, and over time our height decreased and decreased and decreased. So over time our energy decreased, our total energy decreased just a little, not by a lot, but just by a little. Okay, so we can think of why that does. So for the most part, mechanical energy was constant. But there was some loss to something else, and that loss is going to be loss to thermal energy due to an outside force of air resistance. Right, so that air resistance turns some of that mechanical energy into thermal energy. Okay? So then we can look at ULab 2. And again, with ULab 2, we got another graph, so hopefully it looked something like this for you. Obviously, yours was a lot neater. It's tough to write in this app I use for these notes. Okay, so we looked at energy versus position. And we didn't get the linear results that we got up above. Let's see, for KE, you probably got something that looks kind of like this. And for US, you probably got something that looks more like this. And then for your total energy, you probably got something that looks kind of like this with maybe an even larger slope, okay? So you might have seen, most groups saw, that there was a pretty large drop in total mechanical energy. So the question becomes, where did that energy go? We couldn't just destroy it, it just doesn't poof, disappear. So where did it go? And there's a couple common answers that students give. One is that there's friction. And there is, but it's not where you think. It's not the friction necessarily between the wheels and the table. It's the friction between the wheels and the axle. Okay? That friction between the wheels and the table is what allows those wheels to roll. And that is really the source of most of the energy loss. Because those rolling wheels, it takes a lot of energy to get those wheels to roll. Those are really thick, heavy, large wheels. So the energy really isn't lost, it's just turned into what we call rotational energy, okay? To be more specific, rotational kinetic energy. And if you're going to take the AP class, the AP test, and if you're coming in to see me in the early mornings on Tuesdays, we're going to talk more about this. So it turns into, quite a bit of it turned into rotational kinetic energy. A third place where it went is we actually don't have, that's, if you recall, that's a pretty big spring that we use. It's not a massless spring. Okay, so there's some of the energy goes into the fact that we have to move that non-massless spring. And then you might recall that we heard some sound as well as it's rolling across. Okay, so certainly we have some energies that we did not account for, which is why it looks like our total energy increased, but we know that it did not because we know that energy is conserved. So we're going to use these ideas now to solve a few different types of problems. The first problem that we're going to talk about is a roller coaster problem. So example 1 is a roller coaster problem, and these are pretty typical. And so let's go ahead and draw our roller coaster. It might look something like this. This is the, I'm going to call this the American Eagle from Six Flags. And up at the top here, we've got our cart, our roller coaster cart. We're going to say that the mass of this cart is 200 kilograms, and it has an initial velocity of 20 meters per second. And it's going to be, from the ground, it's going to be at a height of 30 meters. I also know that this height from the ground is going to be 15 meters. And I'm going to say that this is right at ground level. So this is right at ground level. This point right here and this point right here are at ground level. Okay? So I want you to find three things. I want you to find the velocity of the cart, at the bottom of the first hill, at the bottom of the second hill, and the top of that second hill. So pause for a second and think about how you would want to do that, okay? And then we're going to go through the problem as well. So let's think about, and let's go ahead and label a couple different points here. I'm going to call this point right here, I'm going to call this point A. Okay, I'm going to call this point B, I'm going to call this point C, and I'm going to call this point D, just so that we can reference those as we're going ahead and doing a problem, okay? Now, when I'm doing these problems, there's a couple things I have to think of first. Because I have to worry about gravitational potential energy, the first thing I'm always going to think about is where is the height equal to 0? I have to know where I'm measuring my height from. So I'm going to go ahead and I'm going to say that the ground is 0, so that right here at point A and right here at point B, since they're at the same height, that's my height equal to 0. That's the first thing I'm going to do. The second thing I'm going to do is I'm going to find a point along the problem where I know everything there is to know. And I'm going to call that my initial starting point. It won't always be the start of the problem. So it won't always be where the roller coaster is starting. Sometimes I know something else. Maybe I know everything that's happening at point A. Then I would say, well, this is my kind of initial energy. That's my starting point. That's where I'm going to start my problem. But for purposes of this problem, and for most problems, I'm going to go ahead and figure out, well, where do I know everything? And in this case, it's right here. It's point D. I know the height at point D, I know the velocity at point D, I know the mass of everything, so I'm going to start there. So when I start this problem, I'm going to start at point D, and I'm going to say, okay, at point D, I'm going to find my initial energy. And we're only going to be worrying about mechanical energy, so my initial energy is going to be the kinetic energy plus UG plus US. And then I can go ahead and fill in, okay, that means that my initial energy is 1/2 mv squared, and it's the velocity at point D, so I'm going to use subscripts to show point D, plus mgh at point D, plus, well, I don't have to worry about US because there's no spring energy in here. So I can get rid of that and not worry about that in the problem. All right. Go ahead and fill in the values for each of those and see what you get for the initial energy. All right, you should have gotten that your initial energy was 98,800 joules. Well, due to conservation of energy, we know that that initial energy has to be the same as the energy every place else along the problem. So at point A, which is my next point of interest, I'm going to go ahead and find the energy at point A. And I'm going to say, and I'm just going to call that E final, energy final. Well, that has to be equal to 1/2 the mass times the velocity at point A squared plus mgh at point A. And then I can plug in what I know about point A. I know the mass at point A. I don't know the velocity. I do know g, obviously always, and I do know the height at point A. In this case, it's nice and easy because it's 0. So this term goes away right away. So now I can say, well, my energy final must be the same as my energy initial. So I end up with 98,800 joules is equal to 1/2 the mass times the velocity of A squared. So go ahead and plug that into your calculator, see if you can figure out what the velocity of A is. Okay, you should have gotten that the velocity at point A is 31.4 meters per second. So pretty simple, pretty straightforward, okay? Let's take a look at the velocity at point B. Well, the velocity at point B, the height is exactly the same. The total energy, the total mechanical energy there is exactly the same. So we can say then that the velocity at point B is exactly the same as the velocity at point A. Point B, however, has a different, point C has a different height. Okay, so when we look at that, the height is 15 meters. So I can use the same process. So I can say, all right, the final energy has to be 1/2 times the mass times the velocity at point C squared plus m times g times h at point C. So go ahead and plug in what you know. See if you can find the velocity at point C. You should have found the velocity at point C to be 26.3 meters per second. So that's it, pretty straightforward. Let's go ahead and let's just summarize some of the important points that we found here. Okay, so let's just put summary. Okay. So the big thing and the idea that lets us solve all these problems is the conservation of energy. So the total energy is the same for the entire problem. Right? It's not going to change. So once I find the energy at one point in the problem, I know it everywhere. The other thing to realize is that the kinetic energy is going to increase as the potential energy decreases. Okay, so we saw that in our lab as well. And that UG, of course, is going to decrease as height decreases. Right, so we keep gaining kinetic energy, so the object goes faster and faster and faster. The other thing, and you can prove this to yourself by going back and changing the mass of the roller coaster. So change that mass to, say, 300 kilograms. You're going to find that the velocities don't change. Because when you're dealing with a roller coaster, the mass often drops out. So I tell you this because on your mastering physics problems, Sometimes they're not going to give you a mass, and you're going to think, well, I can't do this problem without the mass. But if you carry the algebra, if you do the algebra, you're going to see that by the time you get to the end, the mass is going to drop out of the problem, so you're not going to have to worry about it. Okay, so think about that as you are going along and doing some of your problems over the next couple of days. All right, let's look at a second example. Okay, and now let's bring in a spring. So we're going to look at a horizontal spring. So this is very similar to what we saw in our second U lab the other day, where we have a spring and we have a mass attached to it. So we'll just call it M for right now. And I'm going to say that right here was where the stretch was equal to 0. And I've pulled the mass back, so now my stretch, I'm just going to call this S max for right now. And I know if I let it go, okay, let's talk about what happens. So let's just kind of look and see what happens. If I let the mass go from here, think about what forces are acting on the mass, and let's go ahead and take friction out of the problem. So let's just say that this is a frictionless surface. Okay, so now if I let go of the mass, I've pulled it back from its 0 stretch. And remember, it's 0 stretch. We're going to call this equilibrium for this problem because there won't be any forces acting. There will be no net force acting on it, right? Of course, we're still going to have a normal force up and the gravitational force down. But if we're at a 0 stretch, there won't be any spring force because recall that the force of the spring is equal to K times S, right? And if S is 0, there's no spring force. And there's no other force acting on it as well. So now we go out and we pull the mass back and we hold it for a second, right? And then we let it go. So think about what's going to happen to the velocity of the mass as it returns to equilibrium. Hopefully you realize that the velocity is going to start out at 0 and increase as we go to equilibrium. Now I want you to think, what happens to the acceleration as the mass goes back to equilibrium? Hopefully you realize that the acceleration is actually decreasing. And it's decreasing because the stretch is decreasing, right? We start out with a really large stretch. But as the mass goes back to equilibrium, the stretch decreases, so the force acting on the mass decreases. That means the net force must be decreasing and the acceleration must be decreasing. The mass is still getting faster, but the acceleration is actually decreasing. Right when the mass gets back to here, equilibrium, there's no net force, so the acceleration is 0. But the mass still has velocity. It's still going to the left. So as it goes to the left, we introduce another stretch. This time it's a compression. And because the stretch is, the spring is compressing, we know that the force on the mass is actually going to be acting to the right. So now the mass is going to the left, but the net force is acting to the right. So we have a velocity to the left, an acceleration to the right, and the mass is going to be slowing down. Until it gets to a point, somewhere around here, where it reaches its minimum stretch. At this point, the mass is going to have no kinetic energy. It will have slowed down to a velocity of 0. It will have only US, and there will be a large force, a large spring force acting to the right. So now the mass is going to start accelerating to the right. And this is going to continue and go on forever if we have no external forces slowing it down. Now, obviously, in the real world, we know we're always going to have some kind of a friction force or air resistant, something going on with a non-perfect spring. So we don't ever have a perpetual motion machine. That's impossible. But for our purposes for calculations, we're going to assume that there's no outside forces. This is a perfect massless spring, and this mass would continue oscillating between the minimum stretch and the maximum stretch forever. Now, having said that, we can see pretty quickly that the maximum velocity is going to occur right here at equilibrium. Okay, so that's what our first problem is going to entail. Our first problem is going to ask us, okay, if we have a, let's say, go with a 0.7 kilogram mass stretched to 0.2 meters from equilibrium while attached to a spring with a K value equal to, let's just go with 9 newtons per meter, find the velocity at equilibrium. Okay, so I'm going to go ahead and we're going to use conservation of energy, and we're going to look and we're going to say, okay, first of all, do I need to worry about UG? I don't, because the height is not changing. UG only changes when height changes. So since there's no height change here, I don't have to worry about UG. Second, just like the previous problem, I want to identify a point in the problem where I know absolutely everything. And I know everything at this point right here, right at S max. Because I know that S is going to be 0.2 meters, and I know the velocity at S max is going to be 0. So I can go ahead and I can find my initial energy, because it's going to be 1/2 mv at S max squared plus 1/2 k times S max squared. So go ahead and find that value now, okay? Or, if you like, you can carry that along in algebraic form and we can just solve for the velocity, okay? So that's what I'm going to do here. So now that I know that that's just a number, okay, because I know that the velocity is just 0, and I know what k and I know what S max are, I can go ahead and say, well, what I'm really interested in is the velocity at equilibrium. So I'm going to go ahead and find the energy at equilibrium, and I'm going to say, well, I'm going to call that my energy final, and that has to be equal to 1/2 mv at equilibrium squared plus 1/2 k S at equilibrium squared. But I know that S at the stretch at equilibrium is 0, so that goes away. So I'm left with my final energy equaling 1/2 m times the velocity at equilibrium squared. And I have to remember that I've got still to have the conservation of energy, so I can set these two equations equal to each other because the energy initial must equal the energy final. And then I can solve for the velocity equilibrium. So go ahead and do that now. Check your math, make sure, and then come back and check the answer. All right, you should have found a velocity at equilibrium to be 0.72 meters per second. Okay? All right, let's go ahead and let's look at one last type of problem. And this is kind of the toughest. This is going to be example 3. And we're going to look at a vertical spring. All right, so here is a vertical spring that's hanging from the ceiling. And it's going to be a massless ideal spring. And since it has no mass and we're not hanging a mass from it, we can see that the stretch must be 0 and US must also be 0. Now we're going to go ahead, and I'm going to leave myself some room here. Now we're going to go ahead and we're going to take the same spring and we're going to hang a mass from it, and we're going to slowly lower it to equilibrium. So I'm going to draw just a little dashed line here. Okay. And then I can go ahead and I can label and I can say, well, this stretch must be my stretch at equilibrium. So the first thing you should notice is that there's a big difference between a vertical spring and a horizontal spring. A vertical spring, equilibrium does not occur when the stretch is equal to 0. Equilibrium occurs at a stretch that's not equal to 0. Because what happens at equilibrium? Let's do a quick free body diagram here. At equilibrium, we know the net force has to be 0. So if this hanging mass has a net force of 0, then we know that the force down of force of gravity has to equal the force up, which is the force of the spring, which is K times S equilibrium. So we can see that S equilibrium cannot be 0. Okay? Now, for our energy problem, what we're going to do is we're going to go ahead, we're going to take the same spring, we're going to take the same mass, but we're going to stretch it past equilibrium. So same setup. This is our new stretch, and we're going to call that S max, and we're going to let it go. And then we're going to see what happens. And you already know, because it's very similar to what happened with our horizontal spring. Obviously, the mass is going to move up, okay, because right here I've got a very large spring force, larger than the force of gravity, right, because I stretched it further. So we're going to have an acceleration up, so we're going to have a velocity up. And when the mass gets to equilibrium, again, we have no net force, but we still have a velocity up. So the mass is going to go up, right? We're going to have a larger net force down now because that spring force is going to decrease to be less than the force of gravity, so our acceleration is going to be down. So eventually we're going to get to a point here where the mass is going to stop. Then it's going to start going back down, and it's going to oscillate up and down. In our case, in perfect physics world with no friction or a perfect spring, it's going to oscillate up and down forever. And that's why I left a bit of a space here, because I want to go ahead and draw here. I want to draw in where our mass has come to a stop at the top, and we're going to call that S minimum. Okay? And the question we're going to be asked is we're going to find the velocity equilibrium. So find the velocity at equilibrium for a 0.5 kilogram mass that is released 0.2 meters from, and I mean lower, from equilibrium. And we know that the stretch at equilibrium, because we measured it, is 0.494 meters. All right, so let's talk through this a little bit. First of all, unlike our horizontal spring, we can see that we're going to have to worry about UG. We're going to have gravitational potential energy here. So the first thing I want to do is I want to define where my height is going to be 0. Now, I always like to define a height of 0 at the lowest possible point in the problem. And I can see here that that means that the height right here is going to be 0. I'm going to define that. I can pick anywhere I want, but I really like to have all positive heights, because if I have all positive heights, I have all positive UG, and I really don't like negative UG. So I'm going to go ahead and define that height to be height equals 0. Let's talk about then what the height is going to be right here. Well, if I pulled the mass down from equilibrium, which is right here, if I pulled it down 0.2 meters or 20 centimeters, if I pulled it down, that means I went from here to here, and that was 0.2 meters. Well, that means the height here must be 0.2 meters. So now I know heights in my locations of interest. I'm going to be interested in this point because I think this is where I'm going to know everything. And I'm going to be interested in this point because this is where I want to find the velocity. So now I have my heights at each one of my positions of interest. Okay, the next thing I need to do is I need to go ahead and figure out what is my energy at my initial point of interest. So my energy initial is going to be right here at the S max. So I'm going to put this as at S max, is going to be my kinetic energy, so 1/2 mv squared, plus my gravitational potential energy, mgh, plus 1/2 ks squared, and this is the S at maximum. I can see a couple things right away. First of all, I can see that my gravitational potential energy is going to be 0 because I know the height is 0. And I can see the kinetic energy is going to be 0 as well because when I release this from rest, the velocity is 0, so the kinetic energy will be 0. So my initial energy is simply 1/2 k S max squared. Well, wait a minute, there's a problem here. I don't know what k is. But I can find out what k is because we went ahead and we drew this free body diagram. I know what m is, I know what g is, I know what the equilibrium stretch is, so I should be able to find k. So go ahead, do that now, and see if you can find what k is equal to. You should have found that k, and I'll go ahead and put that up here. You should have found that k is 9.92 newtons per meter. Now we can use that, and we can go ahead and plug that into our initial energy. I'm going to go ahead and I'm going to carry that along, though. I'm just going to do the algebra. So now I'm going to look at my final energy at equilibrium. And I'm going to say, well, my final energy is the kinetic energy at equilibrium plus the potential energy at equilibrium plus the US at equilibrium. Now, unfortunately, none of these will be equal to 0, because remember, our equilibrium stretch is not 0, our height is not 0, and our velocity is not 0. We don't know what our velocity is. That's what we're trying to find. But you have enough information now to do that. You can go ahead and plug in S max and K. You can set these two equations equal to each other. So you're going to set this guy equal to this guy. You know the height at equilibrium, you know the stretch at equilibrium, so you should be able to solve for the velocity. So go ahead and do that now. You should have gotten that the velocity at equilibrium is 0.89 meters per second. All right, let's talk, before we leave this problem, let's talk about one other thing. Let's look here, and I would like you to take a guess, okay? We had our mass at equilibrium, and we pulled it down 0.2 meters and we let it go. How high up do you think it's going to go from equilibrium? Take a guess. I bet you can guess the correct answer. If we pulled it down 0.2, how far up do you think it's going to go? And if you're not sure, think back to when we looked at our, I don't know why I can't move my, here we go. When we looked at our horizontal spring. Think about it this way. If we have our horizontal spring and we started at S max and we let it go, let's say I think we pulled this guy 0.2 meters as well. Don't you think it would go 0.2 meters to the left as well? Wouldn't it have to? Because you want the energy, right? Here we have no kinetic energy, all US. Here we have to have no kinetic energy in all US. The only way we can get that is if we have the same stretch. That discussion is a little harder to come by, a little harder to understand. Oh, I'm messing up my notes here. A little harder to understand when we're looking at a vertical spring, but we're going to find that the same thing occurs. We're going to have the same result. So if we pull the mass down from equilibrium by 0.2 meters, we're going to find that the mass goes up 0.2 meters as well. And I want to take a couple minutes and I want to prove that to you so that you can always use that result when you need to. So for our notes right now, we want to prove that SEQ is in the middle of S max and S min. So if we can prove that S equilibrium is S min plus S max divided by 2, we will have been successful. So the first thing we want to do is we want to remember our free body diagram at equilibrium, where we have that mg has to equal k times S equilibrium. Right, so k S equilibrium has to equal mg. We're going to need that later, so we're going to go ahead and keep that in mind. Then let's go ahead and recall that at S max, our energy was all US, so 1/2 K S max squared. Because we didn't have any UG because we defined our height there to be 0, and we didn't have any KE because we know our velocity is 0. Now let's look and see what's happening at S min, and recall that our energy there is going to be, some of it's going to be US, so K S min squared. Some of it's going to be UG, okay, and we're going to talk about UG in a second here. And we're not going to have any KE because KE is going to be equal to 0, right? Because it's 0 velocity up at the minimum. So I want to get rid of this H, okay? I absolutely don't want H in there. I want to have H in terms of S. So let's look back at our problem up above. Okay, and let's use some numbers before we go ahead and just write an equation in terms of H and S. Take a look here. If we had when we had a stretch, okay, of 0.2 meters from equilibrium, our S max was 0.694. Hopefully you figured that out. I'm not, we didn't kind of talk about that directly, but hopefully you see that the S max was 0.694. Okay. You wouldn't have been able to get the right answer for velocity equilibrium if you didn't see that. So our maximum stretch was 0.694, and that occurred right here. Okay. So now if we take that result and we say, okay, if my stretch, my max stretch is 0.694, and I move up 0.1 meter, what's my new stretch? Well, my new stretch is my max stretch minus that 0.1, minus that height, okay? Well, now let's go up 0.2 meters, okay? So my max stretch was 0.694, I went up 0.2 meters, so my new stretch was just 0.494. So I can write something pretty generic, and I can say, well, and let's do that over here. Let's go here. I can say that my S is simply equal to my S max minus the height. Or I can rearrange that and say H is just equal to S max minus whatever S I'm at. And since for this problem, where I'm doing my proof, I'm working at my S min, I can say that H is just equal to S max minus S min. So that's what we're going to go ahead and do when we go down here. I'm going to switch colors, pen. And I'm going to say at S minimum, H is equal to 1/2 K S min squared plus mg times S max minus S min. Then I can set these two equations for energy equal to each other. So I get 1/2 K S max squared has to equal 1/2 K S min squared plus mg S max minus S min. And now I'm going to go ahead and make a couple of substitutions. So you're going to do a little bit of algebra. So this is one of these instances where I'm doing a bunch of algebra and you might not see where I'm going, but trust me, we're getting to the place we want to go. The first substitution I'm going to make is from my free body diagram. I can see right away that mg is equal to Ks equilibrium. So I'm going to go ahead and replace mg with Ks equilibrium here. And I'm going to go ahead and move 1/2 K S min squared over to the other side of the equation. So I'm going to end up with 1/2 K S max squared minus 1/2 K S min squared equal to K times S equilibrium times S max minus S min. Now I'm going to go ahead and factor the left side of this equation, and I'm going to first greatest common factor, so I'm going to take out 1/2 K. And I'm going to be left with S max minus S min times S max plus S min, right? A squared minus B squared is equal to A minus B times A plus B. And then S equal K times S equilibrium times S max minus S min. So hopefully you see some simplifications right away. This guy goes away, K goes away, and I'm left with, and I'm going to rearrange the order here, I'm left with S equilibrium is equal to S max plus S min all over 2, which is exactly what we had wanted to prove anyway. So now hopefully we see that, let's go up to our picture, hopefully we see that when I pull the mass down 0.2 meters from equilibrium, it's going to go up 0.2 meters from equilibrium as well. Whether it's a vertical spring or horizontal spring, I end up with the same result. Okay, sorry for the long notes today. That's it. That's all I've got. Have a great day.